section 9.6. All right, so the first thing that I want to do is just, I want to do an example of how we would sketch a graph of a polar equation by hand. So let's say the problem asks us to sketch r equals 3 cosine theta. So I'm going to grab a piece of my graph paper here, and we will make a graph. So we're going to say this, we're asked to sketch a graph. So what I'm going to do is go back to probably the first way that any of us learned to graph anything, is just make a table of values. So I'm going to make a list for theta and r, and just plug in some numbers and calculate. So, and I'm going to use my unit circle angles, and I'm going to calculate this in decimals for my radius so that I can plot, points. So I'm just going to start plotting points. When r equals, when theta equals, I'll start when theta equals 0. If I plug in theta equals 0, I end up with r equals 3. This cosine of 0 is 1. So I get a point at 0, 3. And then I'm going to plug in pi over 6. I'm just going to use my unit circle angles. Pi over 6, when I calculate that, I get about 2.6. So here we are at 2.6 out there. And then pi over 4, I'm just plugging in and calculating here. So pi over 4, I end up at about 2.1. So there's pi over 4, so there's about a 2.1. I'm just guesstimating approximating where they go. Pi over 4, then we're going to go to pi over 3. And I get about a 1.5. So pi over 3, I'm about here. And then at when theta equals pi over 2, I end up at 0. And then we can keep going. So we have part of it. So I'm going to plug in 2 pi over 3. So when theta equals 2 pi over 3, my radius ends up being negative 1.5. So here's 2 pi over 3, and there's 1.5 and 2 pi over 3, but I go the opposite direction. So I go to here. And then I'm going to go to 5 pi over 6. When theta equals 5 pi over 6, I get negative 2.6. So there's 5 pi over 6. There's about 2.6, and I go negative. So I end up about here. And what does this graph look like it's going to be? Circle. So that graph would be a circle in polar coordinates. So if I was asking you to sketch this by hand, what I would look for is some points like this plotted on your graph, and a sketch to give a good idea of what that shape would be. So this is a circle in polar coordinates, and the diameter is 3. Well, there's some tools that we can use to help us sketch graphs of polar equations, just like there are tools that we use to help us sketch graphs of rectangular equations. We talk about symmetry, we talk about other things that we know about the graphs. We can use some of those tools to help us with these sketches as well to get an idea of what they look like. So let's talk a little bit about how we tell something about the symmetry of polar graphs. Any questions on how we came up with this graph in polar coordinates? Okay. Symmetry. And I'm going to say symmetry about, because we're going to talk about symmetry about various axes. So just like we talked about symmetry about the x-axis, the y-axis, and the origin, we'll do the same thing with polar graphs. So we're going to talk first about the symmetry about the line theta equals pi over 2. Well, first off, what is the line theta equals pi over 2? What are we, in polar coordinates, what are we thinking of there when we think theta equals pi over 2? Like the y-axis, the vertical axis. So theta equals pi over 2 is like the vertical axis. The way we test for symmetry about the line y equals, or theta equals pi over 2 is we replace r theta by r pi minus theta, or minus r minus theta. And after we do some work with our equation, if we get the same equation, then we have symmetry about theta equals pi over 2. Just like one of our tests for symmetry in rectangular coordinates, we replace x with negative x and see if we get the same thing. That test for y-axis symmetry. Same kind of idea. So we replace these things, do some work with the equation. If we get the same equation in the end, then we have theta equals pi over 2 symmetry. The next one is we're going to test for polar axis symmetry. Polar axis, what are we in polar coordinates, what are we thinking of with the polar axis? What's the polar axis? The horizontal axis. So the polar axis is the horizontal axis when theta equals 0. So to test for polar axis symmetry, horizontal axis symmetry, we replace r theta by r negative theta, or negative r pi minus theta. And if we get the same equation, then we have polar axis symmetry. And then finally, we're going to talk about symmetry about the pole. And the pole, when we're talking about polar coordinates, what do we mean when we say the pole? The origin. So symmetry about the origin. We replace r theta by r pi plus theta, or negative r theta. And we get the same equation. And what we're using to figure out if we have the same equation, just as a reminder, we're using our even and odd identities that we talked about last semester. And what that was sine of negative theta is negative sine theta. The sine function is odd. Cosine of negative theta equals cosine of theta. Cosine function is even. Sine of pi minus theta is sine of theta. That doesn't change anything. And cosine of pi minus theta equals negative cosine theta. So we'd be using those identities to decide if we have the same equation. But luckily there's a shortcut that we can use most of the time. So these we have to remember all of this stuff, but there's a shortcut that we can use most of the time. The shortcut is if we have r equals some function of the sine of theta. So if there's just sine theta in our equation, it could be some other things going on with the sine theta, but if it's just sine theta, then we have pi over 2 symmetry. So if our function is just a function of sine of theta, we have pi over 2 symmetry. And if we just have a function of cosine of theta, we have polar axis symmetry. So if we look back at our example that we just graphed, this is just a function of cosine theta. We have symmetry about the polar axis. So what we could have done, if we knew that beforehand, we could have just graphed the top half, and we know it has polar axis symmetry, so we would be able to just transfer the points to the bottom half. So that's one way we can use symmetry to help us sketch graphs. Usually these shortcuts are going to help us out enough to figure this out. Yes?
So,
yeah, so this equation is just some function of cosine theta. There's no sine theta. There's nothing else involved other than a cosine of theta.
Okay.
So it could be something. We'll go talk a little further, but there's just cosine theta in the equation.
Okay.
That means that's what that f means. It's some function of the cosine of theta. It can have other stuff in there, some other numbers, some other things in there, but it's just cosine theta is what our trig function is. All right, questions on our symmetry tests. So some of the equations, some of the problems are going to ask you to test an equation for symmetry about the various axes. But let's look at how we would use symmetry to help us sketch a graph. Okay. So let me grab another piece of graph paper, and we'll sketch another graph. And we're going to use symmetry to help us. So for this one, we want to sketch a graph of r equals 2 minus 2 sine theta. So before we even start sketching, there's just a sine. Our only trig function is sine of theta. So what kind of symmetry is this going to have? It's going to have pi over 2 symmetry. So we can graph the right-hand side or the left-hand side and copy it over to the other side. So we know it's going to be symmetrical about the vertical axis. We can just do half the graph and come up with a sketch. So let's make our table of values, theta and r. I'm just plugging in thetas and calculating. So when theta equals 0, r equals 2. So I'm going to plot a point. Theta equals 0, r equals 2. When theta equals, I'm just plugging in and calculating, pi over 6. So when theta equals pi over 6, I get 1. So I'm going to have a point here at pi over 6 and 1. When theta equals pi over 4, I get about 0.59. So something like that. And then when theta equals pi over 2, I get 0. R equals 0. So there's the top half of my graph. And we know this has pi over 2 symmetry, yes?
So when you're just going to plug in the points, would you just put a calculator and get 25?
Yeah. Yeah. So a calculator would calculate sine and cosine of an angle. And we know that the left half looks exactly the same. So I get a point here, and I get a point here, and I get a point here. So there's the other half of the other top half of this graph. Let me change this a little bit. I want to make it look a little better. And I'm not going to go through and calculate all the points for the other half. But if we completed this graph, if I plotted these other points, I end up with a point about here, a point about here, and a point right about there. So the bottom half of the graph looks like this. The other half would look exactly the same. And we get a graph that looks something like this. This is called a cardioid, because it's heart-shaped. So this graph is a heart-shaped graph. And to get these other points, I would just plug in these other angles and calculate my radius. And that's how I would get those other points. I'm just not going through all the calculations. All right, so now we could have a saying for our math class, right? We could say this, right? I heart polar coordinates. You have to have a lot of math savvy to get that one. That would be a good one. All right, questions on what we did with that graph? Yeah, you're definitely going to have a lot of math savvy there. All right, in your book on page 687, there are these. All we're going to do for this last part is just look at some pictures. So in your book on page 687, they have pictures, and I'm going to put them up here as well. Special polar graphs. We should be familiar, kind of generally familiar with these graphs. Not all the details, but just kind of big picture, what are we looking at? So the first ones. The first ones are circles. Any function, any polar function that looks like r equals a cosine theta or r equals a sine theta is going to be a circle. And a is going to be our diameter. So what I would expect you to know is that if you had something and it said what is the graph of this thing, not that you could necessarily sketch it in detail, but know that it's a circle. A cosine theta, a sine theta. Cosine circle has polar axis symmetry. The sine function circle has pi over 2 symmetry. So that's something you should be somewhat familiar with. Lemniscates. These figure 8 shapes are called lemniscates. They're the only ones where we have an r squared. So I have an r squared and we have a sine 2 theta and an r squared and cosine 2 theta. So those graphs are lemniscates. And notice that this one has polar axis symmetry and origin symmetry. This one only has origin symmetry. So when you have an r squared and a sine 2 theta or r squared cosine 2 theta, you have a lambda scale. All right, let's look at a couple more. These are really nice graphs. These are our limasomes. I meant to do that. There we go. So our limasomes always look like r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. And depending on the relationship between a and b, you can get a loop, you can get a dimple, that's what we call the cardioid. You can get a smaller dimple or just a flat shape. I wouldn't expect you to know this relationship between a and b, but just when you have an equation that looks like this is going to be a limacome. And you can have several kinds of limasomes. And these with that we've graphed here, because they have polar axis symmetry, these would all be the cosine limasomes. And we graphed one cardioid that had pi/2 symmetry, and that was one of the sine function limasomes. So that's another family of special polar graphs. Yes. With the cardioid, this one, the dimple goes all the way to the pole. And with the dimpled one, it just kind of goes in a little bit. And here it's just kind of flat. Yeah.
How would anybody use this ever in their lives?
There are applications where you have functions, where you have something that's described by a function that takes this form, some electrical current, a power function, something that takes this shape, where you have a limacome would describe the behavior of something. But they do come up in various kinds of applications. It's just specific ones, hard to pick out a specific one here and a specific one there, but it does happen. The next ones, and really for me the bottom line is they're just kind of cool. They're kind of like art. Art doesn't necessarily have an application in your everyday life, but it's still fun. So these are all Rose curves. Your Rose curves are always going to have the form r equals a cosine n theta, where n is some number. So here this would be r equals a cosine 3 theta. You get 3 petals. Polar axis symmetry. If n is even, you get twice as many petals as n. So this here n is 4, and we get an 8-petal Rose curve. The sine Rose curves have pi/2 symmetry. When n is odd, we get however many petals. So n is 5 here, and here n is 2, so we get a 4-petal Rose curve. And on Friday we're going to do a lab that has to do with the different kinds of Rose curves. So what I would expect is if you saw something written like this, you would recognize that this is a Rose curve with 3 petals. This is a Rose curve with 8 petals. All right, questions on the special graphs? Now let me show you in your calculator. There we go. We can graph these polar equations in our calculators. So you need to go into your mode, and down here, where we normally keep it set on function, to graph something like y equals x squared, we need to move it over to polar. That's what this is. And then in your y equals window, instead of y equals, you get r equals. And you want to make sure your mode is in radians. So I'm in radian mode. And I can say R equals 5 cosine 3, and then instead when we press this X button here, I get a theta. And then I can graph that. And I get a nice rose curve. And I could change this. If I change that to a 4, I would get an 8-petaled rose curve. So there's my 8-petaled rose curve. 2 plus 2 cosine theta. And there's my cardioid. And we have polar symmetry, so there's that. We could change this to a 2 plus 2 sine theta. We get pi over 2 symmetry. There we go. There we go. That one's upside down from what we did before. So let's turn it over. There we go. And that's the one we graphed part of before. So you can do these. You can do lots of nice polar graphs in your calculator. All right, questions? Okay, homework. All right, there you go.
Really good.
And I double
This is your.